Everyone, welcome back. Now today's topic is on probability generating function. This was questions raised by one of my viewer. All right. Now I'm going to address it shortly. Let's get started. Hi guys, welcome back. This is the questions that we are going to solve today. All right. Now let's read through the questions before we start. Now we have two players play a game with a fair six-sided die with faces numbered 1 to 6. Right? Now in each round of the game, each player throws the die once. Now the game ends if either of the players throw a 6, unless both of them throw a 6 in the same round. Now in which case the game continues. Okay. Now, the total number of throws of the die up to and including the last throw is denoted by the discrete random variable x. Alright. Now, our first task is to state the possible values of x that the random variable x can take. Right. So I hope that is clear with this question. Right. Now I'm going to highlight some of the main point in this question here. Now, first of all, we do recognize that this is a fair die. Fair die means the chances of one number appearing is 1 out of 6. Right. Now, in each round of the game, each player throw the die once. The game ends if either of the players throw a 6. Right. So that the game ends if either one of the players throw a 6. Okay. Unless both of them throw a 6 in the same round, in which case the game continue on. Right. Now the game will end. Just to be sure here, the game will end if one of them. I think if you read it properly, it should say if one of the player actually get a 6, then we have a winner. Right? If both of them get the 6 at the same time during that round, then the game would continue further. Okay, so this is the second part here. Right? And then the total number of throws in that round itself will be counted. Right? Okay, now I'm going to show you a proper way to get a visual understanding of what we are looking at when we play this game here. Okay, now let me build up a table here. Okay, it'll be easier. Here I'm going to label player 1 as player A and then player 2 as player B in this case. All right. And then before we continue any further, I might want to label what does X actually represent. So X represent, based on the question itself, X represent the random discrete or discrete random variable that represent total number of throws. Okay, so X represent discrete, okay, discrete random variable that represent, oops, sorry about that represent the total throws. Okay, I make it short here, right? Therefore, first of all, the x should be discrete, meaning that the discrete value of this random variable can only take integer numbers. Right? So from this table, we are going to discover what are the discrete values that the random variable x can take. Right? Okay, let's imagine. Let's try to simulate playing the game. Right. So take for instance, the first player is going to start. Okay, assuming that the first player fail to get a 6, right? Fail to get a 6, which means the chances of getting other numbers will be 5 over 6. Probability of getting a 6 will be 1 over 6. So before we continue further by completing this table, I like to write down a bit of informations regarding the probability of success here. So I'll label P represent the probability of successfully getting a 6. So it's chances of 6. I just make it short here. Chances of getting a 6, which is 1 out of 6, right? And then whereby Q, for my notation, Q represent someone who failed to get a 6, which is having a chances of 5 or 6, right? Now that will be my notations that I'm going to use to build the probability and discovering the discrete value for this random variable, right? Okay, now let's continue on with where we stopped at just now. So let's assume that when we start the game, player A failed to get a 6, right? So I'll label that as F, whereby player B successfully got a 6. So therefore, the game ended, right? So here we have a winner. Right. Now you can count here by looking at this first round. There are total number of 2 throws. There are total number of 2 throws. So this is one of the possibility. Or I can label. It's possible that when player A throw, player A will be able to get a 6. So therefore, player A would win, provided that player B get a non-6 in this case, or maybe getting a 5, getting a 4, and so on and so forth. Right. So in the second round, for instance, right, you can see that there are also total number of 2 throws there. Right. So these are the only 2 possibility for the game to end with one player winning, right, where in both number of throws of 2. Therefore, I'm going to label this discrete random variable having the discrete value of 2. So I'll label this as x equal to 2. X equal to 2 meaning that in both 2 throws in that round to determine the winner in this case. Right? So I hope that is clear at this point. Okay, think about that. Now next, I'm going to look at, is there any possibility, right, for every round that you play between the 2 players, right? So the second possibility, I would say, right? So here I'm going to start with assuming that the first player fell, and then the second player also failed to get a 6. Right? So if both of them fail to get a 6, then the game would continue. Right? Now we are still in the same round here. Once we continue, we found that player A, for instance, win, whereby player B fell. Then the game ended because we have found the winner already. And then in this case, if you look at this properly, in total, how many throws involved in order to determine or this to come to an outcome with a winner in this case? So there are 4 throws then, right? So this is the game ended with 4 throws. Right? Is there any other possibility? Yes, or of course in this case we could have the first player fail to get a 6, and then continue also fail to get a 6, whereby the second player also fail initially, then they proceed on to the second round, whereby the second round the second player win the game, and then in this round itself we have a winner. Right? So we have a winner. That is the second possibility. Right? Now you are thinking, is there any other possibility? Now let's try to investigate further. Right? And then based on the instruction itself, it says that if both of them get a 6, then the game continue further. So therefore, if both of them get a 6, for instance, in this case both of them win, we can't decide the winner yet, so the game will still continue further. So once it continues further, we could have a winner, in this case player B win, for instance, or we could have the first part of the game both get a 6, so they proceed on to the next section whereby the first player A got a 6 instead of player B. Right? So the game ended here and then ended in this round. So these are the 4 possibility where the number of throws could be 4 times. So they need to throw 4 times uh, between the 2 players. Right? Between the 2 players, the total throws for all the players is 4 to ensure a win in this case. Right? Now, therefore, we will label this as discrete random variable of 4 here. Right? Now, I hope that is clear. Do check out how the possibility of winning if all the players have thrown like 4 times in this case. Right? You can think about that. Okay. Now, next, I would like to explore another sections then. Usually in the exam, like you might want to get more information if you can, even though the first question is just 1 mark. But spending more times in investigating initially will help you to answer the rest of the questions more smoothly in this case. Right? So for me, I would investigate further, like is there any possibility where the games could continue further, right? So I'm going to start off by having both not getting a 6, so they will proceed on, and then once they proceed on, both of them will still get a non-6, so therefore they're going to proceed on further, and then once they proceed on further, yes, we do have a winner here. Okay, we have one winner. That is one possibility, right? Or we could have no one win and then continue on, no one win also, and then instead the third throws, the next throw in this case would be the deciding factor. So from here we know that the first session has ended. In total, how many throws involved for the first sessions to end before a winner can be determined? So there are 6 throws. The same for this possibility, there are also 6 throws. And then don't just stop here. You might want to investigate and explore more. Are there any other possibility? Okay, let's give that a try in this case. So take for instance, we could have first time when they throw, no one get a 6. But the second time when they throw, they get a 6. Both of them get a 6, so they have to continue further. Now, if they continue further, one of the winner can be determined in this possibility. Okay, or we can have no winner initially, and then both of them get a 6. They still need to continue further, and then instead we have a winner here. All right, we have 4 possibilities so far. All right, so do check that out. So we have these 6 throws also. All right, are there any other possibility? Okay, let's try it out. So the next possibility could be initially both of them get a 6. No one win. They are going to continue further. All right. So once they continue further, instead both of them fail to get a 6. So they have to proceed further, and then one of them will be the winner. Hopefully, okay. So this is what we have. Or we could have no winner initially, fail to get, and then one of them will win in this case. All right, that's also one of the possibility. Okay, all right. So I hope that is clear. How many do we have now? We have 1, 2, 3, 4, 5, 6. 6 possibility. Now I'd like to explore further if there are other possibilities. So take for instance, both of them get 6, and then they proceed on. They still get a 6. The deciding factor is at the end. Now, as you expected, we could have this here. So the game ended when one of the player got a win in this case, or got a 6. Right? Now you can see that the last section here all represent the total number of throws that is equal to 6. So therefore, I'm going to label this as um, having a random variable with a discrete value of 6 here, which represent the total number of throws equal to 6 to ensure we have a winner. Right. Okay, do spend some time exploring at this stage. It might take a while, like 1 or 2 minutes, for instance. Yeah, that is fine. Because what comes next will be much more easier and straightforward. Okay. All right. So I hope that is clear. Now next, uh, we have indirectly answered the first question here. So state the possible values of x can take. What it actually says is what are the discrete random values that the random variable can take. So in this case, you can see that it can take x equal to 2, x equal to 4, or it can take x equal to 6, or x equal to 8, and so on and so forth. So therefore, I would label that the discrete value discrete values x can take on 2, 4, 6, and so on and so forth. Of course, all these are multiple of 2 or even number in this case, where the k is positive integer number. Right? And then that is my answer for A there. Okay, so I hope that is clear at this point. Okay. All right. Now next, I'm going to move on to section B. Let's see what do we have for section B here. All right. Now you can see that section B. Let me highlight that. We will still need our informations here. So we need to show that the probability of x equal to 2 is actually given by 5/18. And then next we're going to find the probability of having x equal to 4 here. So there are two tasks that we need to perform. First one, and then the second part here. All right. So I hope you're clear with that. Okay, so if you're okay with that, now I'm going to work out the probability of x equal to 2. Right now we don't need this anymore. Let me clean this up. Okay, so the table of result that we have obtained is very useful for us to determine the probability of x equal to 2 here. Right now, for the first part, probability of x equal to 2. Now it's quite obvious from the table itself. The two possibilities. The first possibility says that one of the player failed to get a 6. The second player managed to get a 6. So therefore, fail to get a 6 will be 5/6, and then manage to get a 6 will be 1/6 there. So that is one possibility. Or it could be the second possibility here. That will be a win, and then not getting a 6. Now you will notice that both of these are the same numbers actually. So it's the same as 2, 5, 6, 1, 6. You can leave it as it is at this point, of course, but we need to prove that it is equal to 5/18. Of course, if we try to simplify this, yes, definitely is 5/18 here. So the first part, yes, we can just write down. We managed to prove that. Okay. Now I hope the first section is clear. Okay. Now the second section. Px probability of having an x equal to 4 here. This is question B. So having a 4. We are going to refer to the second sections in the table itself. We could have this section here. And now I'm going to try to make it easier for us to calculate this. Right? Now you can see that the F actually stands for failing to get a 6 in this case. So the chances of failure will be 5/6 in this case. whereby W represent the chances of getting a 6, which is 1 over 6 here. So we can see that these are all the possibilities that we have, okay? And then therefore we can actually write down one after another. Okay, now take for instance the first possibility. I would have okay, so failure to get a 6. I have 1, 2, 3, 3F there. 3F means there are 3 failures there, and then 1 win. There's 1 6 there. And then the second one is also the same. You will notice that this is also 3 failures, 1 win. So therefore, that would be okay. So to ease the work, I can actually write down this. Okay, now there's the second possibility. The third possibility will be a win 3 times. You can see that here, 3 times here. Let me just label that. 1, 2, 3. 3 win, and then 1 failure. This part is 1 failure here. Okay. So therefore, 3 win, and then 1 failure. And then the same goal for the last possibility. We will have 3 win, and then 1 failure. Now, of course, it's quite obvious to you. Some of this number is double, like this part here is twice of that. And then this is also twice of this. Okay, now from here, of course, if you have calculator, you can just key in and then you will get the answer directly, right? Now, like for me, most of the time I don't carry calculator with me, so it's also a good time for you to practice on your algebra. In this case, we can take it slow and easy. In this case, you notice that we can actually factorize this. Okay, and then there you have it. Now you notice that the first term is actually 5 over 18. So therefore we can actually write down 5 over 18. And then this term here, if you simplify that is actually 26 over 36 there. So which is 13 over 18. Alright. Now of course, because we need to finalize the answer for this, therefore we can write this down as like 65 over let me say 324. That should be correct. Let me see, 16 222. Yes, correct. So 324. So it should be 65 over 324 there. Alright. So I'm going to pause here for a while. You can do your calculation and then you can check back with this. Right. Now once you're satisfied with this, I'm going to show you the next 2 sections, which is the subsections of C and D. Alright, stay tuned. Alright, now before we proceed on to question C, I would like to work out the probability of x equal to 6, since I have already shown you all the possibility here. So might as well we get the probability for x equal to 6 here, just for learning purpose, right? Which is not required for question B. So here I'm going to write down how to find the probability of x equal to 6 here. Right? Now I'm going to make a little bit of simplification so that it's easier for us to work with. So here I noticed that these 2 pattern is more or less the same, because they are like 5 failure, 1 success. So therefore I'm going to write that as 2 times, because there are 2 of this. They are like 5 times failure, 1 time success. Right. And then I'm going to proceed on to the next one here, which share the same pattern also. You can see that this one is 3 time win, 3 time failure, and then which share the same pattern as these 2 also. You can see that this is 3 time win, 3 time failure. So there are actually 4 of that repeated pattern. So therefore I'm going to write that down as failure 3 time, success 3 time. Okay, now that's how it look like for four of this. And then lastly, I will have the last pattern here, which repeats itself twice. So here I can see that I have 5 times success and then 1 time failure. And then there you have it, right? Now, of course, if you have calculator, you can key in everything, and then you should be able to find the probability for x equal to 6. For me, I would tend to factorize that. Okay, now I notice that there are 2, and then I can factorize this. Definitely, I can factorize these 2 out. And then once I did that, I will get this. And then this part will be like, let me see here. I will have 1, 6 here. 2 actually. Yeah. And then finally I will have 1, 6 of a 4. Alright. Alright. Now if you notice that this section here, I would say this expression inside the bracket looks very similar to x4 plus I would say x4 plus 2x squared y squared plus y4 here, which can be factorized as x squared plus y squared here. Now because of that, I'm going to make use of that identity from algebra to simplify this. Therefore, it should look something like this. Now my outside expressions, of course, I can reduce that as 5 over 18 that we have already obtained. The internal expressions would be 5 over 6 squared plus 1 over 6 squared based on this identity here. And then don't forget you have to square this. Yeah, this is square. So from here, I'm not going to like get the final answer in the fraction form, but I rather leave it as a product. Okay, sometimes more is better, right? In this case, I would say, right? So from here, you notice that there is actually 13 over 8 squared. So I hope that is clear. And then from here, I'm going to write down all the result I have obtained so far from for B. So for B, we have already obtained Px equal to 2, which is given as 5 over 18. And then we have also found that probability of x equal to 4, which is 5 over 18, 13 over 18. And then now we have discovered another x equal to 6, which is 5 over 18, 13 over 18 squared. Alright. Okay, I'm going to pause here. I'm going to proceed on to question C shortly. Alright, now based on all the results that we have obtained so far, I would like to summarize that again. Now, so far we have found the probability of x equal to 2, which is equal to 5 over 18. And then we have also evaluated the probability of x equal to 4, which is equal to the product of 5 over 18 multiplied by 13 over 18. And then finally, this is the extra one. I have calculated the probability of x equal to 6, which is given by 5 over 18, 13 over 18 raised to the power of 2 there. Right? Now, the main reason why I need all these values is because I need to prove the next section. So the question C here, I need to show that the probability generating function x is given as such. Okay, using all my previous result that I have obtained here. Right? Now for that, before we start to get the probability generating functions, we need to go through the definition. Okay, so before we start, let me define my GT as the probability generating function for x in this case. I just make it short here. And then by definitions, the probability generating functions for x is given as in a compact form as such. And then the x value for our example in this case is start from 2 and then go up to infinity in this case, right? Now you can write in the explicit form as such. So that is typically x equal to 2 t squared, x equal to 4 t4, and then x equal to 6 t6, and so on and so forth, right? And then you'll notice that we have found a probability of x equal to 2, which is 5 over 18. So I'm going to write down that as 5 over 18 t squared here. And then this part here, we have also found the answer previously. And then x6 is extra. Do I really need to find out x6? Basically, in the exam, due to time constraint, you can ignore x6. Yeah, for me, I just want to confirm the result more firmly in this case. Okay, and then there you have it. This is a geometric progression. You can see that this is a geometric series. It has a common ratio. All this has common ratio. Now before that, for me, I would like to factorize it usually. Okay. For me, I would prefer to factorize in such a way so that it's easier to perform the sum to infinity. Right? This one actually go to infinity. Okay. Now that would be, let me see, I have 13 of 18 t squared, and then I have 13 over 18 t4. Did I get it right? Let me see. Okay, 13. Oh, this is square. Sorry, I missed that out. Okay, and then there you have it. So from here, it will look clearer to us that the common ratio is 13 over 18 t squared. Therefore, by using the sum to infinity formula, now the sum to infinity formula, I just write it down here, sum to infinity formula is actually given by a 1 minus r, whereby a is the first term here, this is a, and then the r in this case, for our case, is 13 over 18 t squared. That is our common ratio. Now from there, we just need to substitute into that formula. So for this, it will be 1 over 1 minus the common ratio. Okay, and then from there onwards, you just need to simplify that. Here it will be 18, 13 t squared, and then therefore, yes, we have successfully proven that the probability generating functions for the discrete random variable x is given as 5t squared over 18 minus 13t squared. Alright, now I hope that is clear for this example. Okay, do take your time to work out the probability generating function. Right. Now next, I'm going to move on to D shortly, which is our last section. Alright, now our last section is D. Here the game is played twice. Use the probability generating functions that we have obtained previously to find the probability that the total number of throws is 8. Okay. Now, first of all, we do make assumptions that the two games are independent to each other, so they don't influence each other in the game. So therefore, we can actually work out the new probability generating functions that represent the situation where the games are played twice. Okay. Now for that, I'm going to let ht to represent the probability generating functions for y, okay, where the y represent the discrete random variable, I just write it in short, discrete random variable that represent, I just make it short, represent total throws when the game is played twice. Alright, now that is my y here. Right? So for this, because the games are independent, therefore, by definitions, the new probability generating functions for y can be written as the, before that, let me show you what does y actually represent in terms of the variable x here. So y is basically represented as the sum of the total throws from the first game and from the second game, which are independent to each other. And then from here itself, we can work out the probability generating functions for y, which is given as oops, I always write this one down wrongly. It's supposed to be x1 multiplied with g x2 here. Okay, because they are independent, therefore by definition it is the product of the two probability generating functions, and then these two are exactly the same. So it's from here. This is g. Okay, I think I used the wrong symbol here. Just let me correct it so that you don't write this one down in the exam. Sometimes when I write x and y, I keep on having the thought that I need to use x in this case. So whereby this is supposed to be a probability generating function in terms of t. I will rather write down as g1t. Sorry. So g2t, whereby the probability generating functions that represent x is given as such. I just rewrite that one more time. Okay, so this is the product of the two probability generating functions that represent x. So g1 is the probability generating functions that represent the game is played once, and then this is the second game. Okay, from here we can basically these two are the same, so therefore it will look something like this, squared, or you can keep it as 25 t4 18 minus 13 squared, squared, right? Now that will be our probability generating functions that represent the game that is being played twice here. But how are we going to make use of this probability generating function y then to find out the probability when the total number of throw is 8? Okay, this is how we're going to use it. Now, by definitions again, probability generating function for y is actually given as y here. Okay, now there's a bit of adjustment that we need to do here. Since the games are played twice, we know that the random discrete values for x are 2, 4, 6, and so on. Therefore, the discrete random values for y must be a 4 because it's played twice. Therefore, the random variable for y would be a 4, an 8, and then 12, and so on and so forth. Therefore, you can actually write this one down as 4 until infinity. And then for that, we can rewrite as py equal to 4 t4 plus py equal to 8, because the second one is 8, T8. And then of course I can proceed on with the rest, like 12, T12, and so on and so forth. Right. So if we are able to expand our probability generating functions in this form in terms of polynomial, therefore we will be able to identify the coefficients for that T8, which represent the probability of total numbers of throws equal to 8 here. Now, how are we going to do that? Okay, very simple here. Now, I'm going to consider this probability generating functions. We can rewrite as, just rewrite this one more time. Now, this one can be written as such. I think I simplified a bit. Hold on, just let me make a bit of adjustment so that it's easier for us to work out the expansion in a while. So in this case, I would rather simplify it this way. That will be 18 square. You can actually factorize out the 18. So it looks something like this. And then that will be 25T4. This is 324 that we have already worked out previously. And then this expression, the denominator, can be written in this form, -2. Right. Now from here we can perform the binomial expansions for this expression here. Now therefore if I expand that, I would get, okay, I'm going to write down the expansions over here. Okay, it's a rather challenging expansion, I would say, in this case. So that will be 1 plus, okay. Now for me, when I do the binomial expansions, I just need to take this number for the second term, this number multiply with this. That will actually give me, oops, just let me change it a bit. That would be 13 over 9 t square. Okay, that's the second one. And then the next one will be -2, -3, or 2 factorial. If you still remember the binomial expansion in this case. And then the next one will be -13 over 18t square here, right, because there's a the third term. And then of course you can proceed on further, but here you don't really need to proceed further because the term that we need is this term t to the power 8. You can see that from here we have t to the power 4 with another 4 outside there that will yield t to the power 8. Okay. Alright, now I'm going to pause here for a while. I'm going to proceed on with the binomial expansion, and then I'm going to complete that and by finding out the probability of y equal to 8. Okay, then pause here for a while. Alright, this is where we are. I just recopy the result that we have obtained previously. Now the first part is the definitions for the probability generating functions that represent the discrete random variable y. And then it can be obtained from this expansion using binomial expansion. And then I'm going to simplify this further. We have okay, so from here we have 13 over 9. And then of course in this case we have like we have a 3 in this case. Is it a 3? Yes, correct, it's a 3. I just write down 169 there. 324 T4. Okay, and then from here what we are interested in is basically, just let me rewrite that neatly first before I summarize the answer. So from here itself, I will get 169, 3131308. Okay. Now, therefore, the probability based on the comparison between this equation here, this equation, and the result that we have obtained here, we can summarize that by saying the probability of y equal to 8 is the coefficients for T8. So the coefficient for T8 is basically this. If you expand this, you get T8. That will be 25 over 324 by 169 over 108. Okay, now that will be our probability, right? That's a huge number to tabulate, of course. All right, so this one I really need a calculator on this, right? So just let me give that a try, and then let's see whether it works or not. Okay, so this is okay. So if you tabulate this, you can leave it in terms of fraction. Based on my calculator, is indicated as 1207, or you can leave it in three significant figures, usually in the exam, right? Okay, and then there you have it. We have successfully answered these questions that is related to probability generating functions. Okay, I hope this is helpful in your learning. Until I see you again, do enjoy math like how you enjoy a piece of cheesecake. All right. Until I see you again. Take care, everyone. Thanks for watching. If you like the video, don't forget to click the subscription button and then the notification bell so that you can receive the latest video. Until I see you guys again. All right. Take care, everyone.